Okay, yeah, thank you for the introduction. And yeah, so as Professor Scoville said, this is the final lecture of this series exploring connections between particle physics techniques and applications in condensed matter physics, or condensed matter techniques and their applications in particle physics. So this is more of a seminar style talk. So this will be applying some of the ideas I discussed, especially last time with generalized symmetries, to some contemporary research, in particular this exotic new state of matter called fractons. Okay, so let's begin. Okay, so this is the outline of this lecture. So first, I will explain what fractons are, basically. And then I will look at two different methods of getting fractons. So in particular, this first one, we will try to get fractons from higher form symmetries. And this will be a particular application of what I discussed last time. But I'll also, for anyone who wasn't there, I will also review the key ingredients that go into this construction. And then the second topic is something a little more exotic, which is another approach to fracton physics, where we obtain some properties of fractons from non-Riemannian double field theory. So I will go through that as well. And then finally come back to the question of what fractons really are. Okay, so first of all, what are fractons? So fractons are particle excitations with restricted mobility. So what we mean by that is, so a fracton is a particle that cannot move in any direction. Its mobility is restricted. There are also other terms associated with this, such as linons, which is a linon is a particle that can only move in one direction, and this one direction would be, say, up and down here, but it cannot move left and right. Now, how could this possibly come about? So the conventional viewpoint on this is as follows. So we can understand the motion of a particle as the creation, annihilation of some kind of dipole operator. So we have some particle here, and then in particular, if you imagine this particle as existing at some site in a lattice, and then if we act with a dipole operator, this would annihilate the particle on one site and then create it on an adjacent site. And then the result of that is that this particle has moved to a different site.
So this is a way to describe a discrete motion. So jumping from one side to the other. That's
yeah. So initially, I'll talk about this in a second, but initially these were found in lattice models. So motion between sites is discrete. So yeah, so in that context, if you annihilate a particle somewhere and create it at the adjacent place, then that's acting with a dipole operator. But if your theory is such that, or the situation is such that dipole number is conserved in a particular direction or in whatever direction, then the particle cannot move in that direction because it would violate the symmetry of the system. And similarly, if we consider starting with a dipole, like say some positive excitation and negative excitation, could be an electron hole pair in a lattice or some charged particles, then we can move them by acting with a quadrupole operator. So, and similarly, a dipole cannot move if the quadrupole number is conserved. So there can be various, in principle, there could be various multiple conservation laws. The simplest case in some simple models would be we only have dipole number conservation. So a single fracton cannot move, a single particle cannot move, but a dipole of two particles could move. So since their discovery, first in 2005 and then again in 2011, various fracton models have been identified in the literature. And these all have essentially, we have something like the Heisenberg spin model that I wrote down a couple of lectures ago. And these have like A sites and B sites on some lattice. And you have some combination of spin operators. These are Pauli sigma matrices on these different sites. And the same with these two cases. So you can actually get fractons arising from very simple situations. And in practice, the restriction mobility can also be associated with a large energy cost for removing the excitation. So, for example, in order to create one, if you cannot create a dipole, then you have to create a quadrupole, which means you need to create 3 more, and there's an energy cost associated to that. And if this is present, this kind of situation is often referred to as fracton order. And that's the situation where you characterized by the presence of defects in your theory that have restricted mobility. And these defects may have a mass gap. So for example, this X cube model and also so-called foliated field theory has a mass gap, or they can be gapless, for example, disclinations in solids. So that's when you have a lattice and at some point there's an angle deficit. And that point, that center of that angle deficit cannot move in any direction. And one other feature of these fracton models is that there's usually a large ground state degeneracy. And then, so far this is on a lattice, but then if we are interested in the continuum limit of these theories as some kind of macroscopic coarse-grained description, the continuum limit of fracton models usually require some exotic field theories.
I want to ask about the ground state degeneracy. So what I am understanding now is that in the screen you can see many of the Pauli matrices, right? And also in topological field theory, we have a similar description, and also the topological field theory has a large ground state degeneracy. But in this point of view, I don't know how the ground state degeneracy emerges. So how can I understand that?
So it emerges from, so if we go back to, if we go back to this picture here. So one conventional picture is that we have something called subsystem symmetries. So they're symmetries that are defined on each plane of the lattice or in each direction. And with this very large number of symmetries, you can think of like if you could do like something like you could do some rotation on one plane of the system while preserving that symmetry, and you can do that for every plane of the system. So you have some degeneracy that grows like linearly in system size or something like that.
So is it due to the symmetry?
Yeah, because you have a lot of symmetry. Okay, so usually, So when people try to write down a continuum description of these, they end up, one way of doing that is to have some exotic gauge theories, in particular some higher rank gauge theories. So some gapless fractal phases can be described using higher rank symmetric tensor gauge theories. And a very well-known example, or very common example, is the so-called scalar charge gauge theory. And in this gauge theory, we have the time component is scalar. There's this field phi. And then the spatial component is a symmetric matrix Aij. And then this would have some U1 gauge transformation, where the time component transforms in the usual way. So it transforms as the time derivative of some scalar function, gauge parameter. But then the spatial part transforms as two derivatives. But with this, we can write down electric and magnetic fields through various combinations of these components. So we have an electric field Eij, like this, and also a magnetic field like this. And with these, we can write down a Maxwell-like Lagrangian, which, for example, in 3+1 dimensions, you have something like that. If you go to different dimensions, then the number of indices in the magnetic field will be different, but it's the same sort of idea. And then if we want to couple this theory to sources, then if we consider some density rho and some current Jij, which has two indices, we can introduce a Lagrangian like this. And then there's a slightly unusual conservation law where the time derivative of the density plus di dj Jij vanishes. And this theory, or such a theory, would have two types of conserved charges. So one is the U1 charge. This is a U1 charge. And then we also have or if you like, this is a monopole charge. And then we also have a dipole charge, like this. So this Q generates an ordinary U1 symmetry, and Qi generates a dipole symmetry. And if we then define a U1 current whose zero component is this rho, and a dipole current that has this particular combination of rho and Jij entering into it, and is related to the spatial component of the U1 current as well, then each of these is individually conserved in the usual way, or each of these being conserved implies this first equation, provided that these components are related. So this kind of construction is the first thing that people did when trying to understand fracton models. But this is kind of bespoke. So this understanding has some limitations. As the first fracton models were just very specific examples and identifying fracton properties in these specific situations. But we want to know if there's an underlying principle behind what's going on here. And the dipole symmetry is gauged in this example, which means it's a redundancy of the description. So it's unclear what this means. What this means physically, like what is the physical role of this dipole symmetry? So it would be nice if we can formulate this in terms of a global symmetry. And And in addition, we have a symmetric tensor field. And of course, symmetric tensor fields appear in gravity. And there have been some proposals that gravity may emerge from the collective dynamics of fractons. And we may consider whether there's a framework for gravity beyond the usual Riemannian paradigm that encompasses this fractonic behavior. And we will get to that later. But first, I will talk about this global symmetry point of view. So I should say, are there any, this is a lot of different things, but are there any urgent questions so far?
And yeah, so here I didn't understand like how fractals are coming in this field. It is like if I take this theory and just write all the possible states and there will have some kind of state that will be corresponding to some particles which are like fractals.
Yeah, that's it basically. So it's yeah. So the fractons here would be these source objects would have some fracton behavior. Some kind of. I think there is something like a solitonic state. I don't quite remember the details, but there's some excitation you can write down there.
Here the sources rho and ji. They are so. I mean, when we have coupled theories like with mu, like whatever gauge fields there were, right? It's coupling to some other fields that from there we'll have all these sources.
Yeah. So for example, this rho and jij, we could write down, for example, like a scalar field theory, like a complex scalar field theory, with that, for example, doesn't have the standard kinetic, like two derivative spatial kinetic term, but it has some higher derivative, like some four derivative term.
For that, we write all this. We just construct all these sources and write theory like this.
Yeah, exactly. So in that you can write down, you can obtain jij. It would be something to do with this. You have some, like, for example, it's not exactly this, but something like di dj phi, or something like that. And you have some other linear combinations. And from that you can, so in the same way as, I guess you were here yesterday, so like from the variation of the action for such a theory, you can as we do in the standard case, where we group some part of the variation into something that we call the conserved current, we can do the same thing with this higher derivative theory. So including further terms.
A derivative from the Lagrangian, from there we have something like j mu. We cannot have a single derivative because from there we'll have j mu kind of thing that we don't want here. That's the reason that in the
in these theories, I guess I guess the fact that you don't have these linear derivatives is related to this dipole conservation. But then, yeah, since the derivative is associated with the spatial variation of that.
This theory describes a fractal in the sense that this particle doesn't have a kinetic term.
This so if you think of it like this is like the electromagnetism of fractons, but usual electromagnetism is for electrons and positrons. This is like the electromagnetism for fractons. So your sources would be, as I was saying, like this. If you have some scalar field that is missing like a usual two derivative kinetic term in some part, but has like higher derivative terms, then that you can show explicitly that has a dipole symmetry due to the absence of this term.
In the previous slide 7. So this gauge transformation makes space-time to split 3+1.
Yeah, this it splits space and time. Yeah.
Okay, so this AI and IJ index is only completely spatial.
Yeah, I should emphasize. I will use I and J for spatial indices here.
So with these two transformations, can we form some kind of a vector which is invariant under this gauge transformation.
So like a 4-vector, for
Yes,
example.
exactly.
So we can, I mean, actually one thing you can do that I won't talk about here, but something I've looked into is you can, and other people have done as well, is like you can construct some A mu nu out of this, like some like rank 2 symmetric field. But actually later on I will also answer your question in another way.
Okay. Thanks.
Okay, so right, so the next part is one way to more systematically construct fracton gauge theories, and that is by using higher form symmetries. So first I'll review some things that I talked about before in this course. So usually we can understand symmetries through the Ginzburg-Landau paradigm, where different phases of matter are connected via phase transitions, which we describe with where we have some order parameter that usually when that order parameter has a non-zero vacuum expectation value, that corresponds to spontaneous symmetry breaking. So you can think of like a complex scalar with a mixing hat potential. And then if in the broken symmetry phase, then the theory is the field is lying on the rim of the hat and it has a non-zero expectation value. However, in condensed matter physics, people find many exotic phases of matter that seem to defy this usual property. For example, so-called symmetry-protected topological phases. Also, things like fractional quantum Hall systems, and fractons are also something like that. But it turns out that by generalizing the notion of symmetry, as I talked about last time, we can also try to describe and understand exotic phase transitions and exotic phases of matter using this within the Ginzburg-Landau paradigm. And for some topologically ordered phases, this has already been accomplished via spontaneous symmetry breaking of higher form symmetries. And the key thing I want to explore, I want to introduce in this part, which is the first main message of this talk, is that gauge theories, such as what I described for gapless fracton phases, can be constructed systematically from spontaneous symmetry breaking of higher form symmetries that do not commute with translations. And I will call these non-uniform higher form symmetries. So this is what I will build up to. And let me introduce a bit more some of this terminology. So I explained this yesterday, but I'll just briefly review some key points for people who weren't there. So in the modern perspective of symmetry, so a theory with a global symmetry under some symmetry group G means that there exists some topological operators U of G on some manifold M, on some closed manifold M, where little g is an element of the symmetry group. And topological means that that its correlation functions are unchanged under deformations of this manifold, unless the deformation crosses a charged object. So we have two types of operators. We have topological operators on some manifold, and we also have charged objects. And for a zero form symmetry, which is an ordinary symmetry, for example, U1 symmetry, with a conserved charge Q, then this operator is just the exponential of I alpha Q, where alpha is some is a parameter. And then we can take this manifold to be, for example, a spatial slice extending to infinity. And then the charged objects are just particles. but for a p-form symmetry, then this operator U is defined on a lower dimensional manifold, so a d minus p dimensional manifold, where here little d is the spatial dimension. If we have a d space on one time. And the charged objects are p-dimensional objects. So for example, for a zero-form symmetry, the charged objects are particles, and for a one-form symmetry, they are lines or strings or whatever you want to call them. And also for a two-form symmetry, you have some membrane is the charged object, and so on. So what are the essential properties of higher form symmetries? How do we define them? One thing is that the set of operators, of these U operators, these topological operators, they have to preserve the group law of the symmetry group G. So UG1 times UG2 should be equal to some other U of G1 times G2. There's one thing I didn't get to talk about yesterday, and that's non-invertible symmetries. And that's the case where the symmetry is not a group anymore, because there's no, so in a group, every element has to have an inverse, but there can be cases, and there are cases in condensed matter physics where there's no inverse. So the closest you can get is G times kind of pseudo-inverse G is identity plus some other stuff. And in such a case, so that is the case, I think, in like anyons and these some exotic systems in low dimensions. And in such a case, then the right-hand side would be a sum of elements. And okay, so then the second property is that there are charged operators. These correspond to our charged objects that are on p-dimensional closed manifolds C. And these are transformed non-trivially by these topological operators whenever on these manifold M, whenever M and C are linked non-trivially in space-time. And if we want to project this down to a spatial slice, we can relate this to like equal time commutators. So if C lies in the spatial slice, then WC is an operator acting on the Hilbert space and projecting M down as well. Then we have an equal time commutator, and this will take this kind of form. So if we have this object W, this operator WC for this charged operator, if I put this U, if I act with U inverse on both sides, that goes away, and then you have U inverse. So that's just a transformation of this. That's just a unitary transformation of this operator, and this will be in some. This will then give some transformation of the charged operator under some representation of the symmetry group. And this representation turns out to be to some power, which when we project onto the plane is the intersection number of M and C in this spatial slice. But if we allow them to, if we don't project down, then this would be the linking number of these two manifolds. So yeah, so we have something like the usual symmetry transformation rules, but just phrased in terms of these topological operators defined on various manifolds. So as a simple example of this, which I discussed yesterday, but I'll just review it briefly. In Maxwell theory, in pure Maxwell theory on d equals 4 spacetime, and in particular, if we ignore sources, then there are magnetic and electric one-form symmetries generated as follows. So the magnetic one-form symmetry charge is the integral over a spatial slice of the Faraday tensor of the electromagnetic flux. And similarly, the electric one is the integral over the Joule of flux over a two-dimensional closed manifold. And the corresponding, so for a zero-form symmetry, we have a one-form conserved current, but for a one-form symmetry, we have a two-form conserved current. So our conserved currents are just the electromagnetic flux in this Joule. And then the corresponding conservation laws are simply the Bianchi identity for the magnetic one-form symmetry, and also Maxwell's equations in the absence of sources. So d star f equals 0 for the electric one-form symmetry. If we have sources, we have a similar situation, but then we just are explicitly breaking at least some part of this electric one-form symmetry. And then the topological operators here are simply obtained by exponentiating these magnetic and electric one-form charges. And the corresponding charge objects are 't Hooft loops and Wilson loops that represent world lines of magnetic monopoles and electrically charged particles, respectively. And then, in addition, as I mentioned yesterday, the U1 gauge bosons can be interpreted as Nambu-Goldstone modes of one-form spontaneous symmetry breaking. So this is one example, and I will show another example, which is the fractional quantum Hall effect. So if we consider a situation where we have some electrons that are confined to move in, say, the XY plane in some system, and then we apply a magnetic field in the Z direction, then the conductivity is, so the relation between the electric current and the electric field is in general a tensor called the conductivity, and the XY component of that tensor is the Hall conductivity, which of course relates the electric field in the X direction, for example, to the current in the Y direction, due to this magnetic field in the Z direction. And this will take some value, which is quantized. And often, in many situations, this is integer quantized. But in some materials, this number nu can actually be a rational number. It can be a fraction. And this situation is the fractional quantum Hall effect. And it turns out this can be described by 2+1 dimensional Chern-Simons theory, which has this action. So it's some integral over some k is some integer called the level of the Chern-Simons theory. That's not so important to this talk. But then we have a dA. And the equation of motion of this, and this A is a one-form vector potential, so it's like something like a usual vector potential. But the equation of motion is very trivial, or looks very trivial. It's just F equals so the field strength defined as dA, the exterior derivative of A, is 0. So from this we can see that we have a two-form current J, which is, if we define J as star A, then this two-form current is conserved because dA is 0, which means that d star J is 0. And if you remember from last time, that's another way of writing current conservation. So we have this conserved two-form current, which means we have a one-form symmetry. And it turns out that due to the discrete integer property of this theory, that this is actually a discrete one-form symmetry with gauge group ZK. So there are discrete allied transformations modulo k. And then the Wilson loops, which are the charged objects of this under this one-form symmetry, when we exchange them, it turns out they obey fractional statistics because we have some phase factor that's related to the number of exchanges divided by k or something like that. And then that means that our statistics are what people call new valued statistics, and these can be rational valued. And this is the origin of this property here. And the corresponding particles are called anyons. So they're something between a boson and a fermion. Because, so for example, if bosons have plus statistics and fermions have minus statistics, this is you can have some complex phase in between in 2 dimensions.
What is the ZK symmetry in this setup? Is it multiplying the base vector dynamics, or
it's the residual, yeah, it's the residual gauge symmetry that you have due to this Chern-Simons quantization. Okay, so that was just some examples. So
what is the number of Boltzmann boson for that reason?
In this case, there would not be any because it's a discrete symmetry. So I guess because you get number of Goldstone bosons for spontaneously broken continuous symmetries. Okay, so that was an overview and reminder of higher form symmetries. And now I want to introduce this term non-uniform symmetries. So we can describe a continuous symmetry as uniform if its current satisfies this commutation relation. So where P mu is the momentum generator that generates translations, or the momentum operator, and J of x is the current. So if this commutation closes down to partial mu j, then the corresponding charge will commute with space-time translations. So this is a uniform symmetry, and then simply a non-uniform symmetry is we can define as a continuous symmetry that does not commute with space-time translations. So a commutator of P and Q is non-vanishing. And this is actually a very standard thing. So simple examples of non-uniform symmetries are just rotations and Lorentz boosts, for example. So with this, let's consider the following symmetry algebra. So if we just have non-uniform ordinary zero-form symmetry, such that we have two charges, Q and Q prime, and we consider this commutation with px, so translations in the x direction. So the commutator with Q prime closes onto Q, and then Q itself commutes with all translations. And then we can write Q as the integral over some spatial manifold of star j, where j is some current. And then we can also write Q prime as the integral over spatial manifold of star k, another current. So this so Q and correspondingly star j generate a uniform symmetry. So what I want to do is I want to show that the world line of a particle charged under Q, due to this non-trivial commutator involving Q prime, cannot move in the x direction. So the world line cannot have a trajectory in the x direction. So to do that, we can first decompose this non-uniform yet conserved current K as follows. So we can decompose it into some, or in particular, we decompose the dual of K, so star K, into star of little k minus some x position times star of j. And then this K here, where we do this such that K is uniform but not conserved. Yeah, because we know that J is conserved like this, and then K, capital K was conserved, so we have this, but then this means that little k is not conserved because this minus this is 0, so this is non-zero. And with this, so in a sense, we've kind of gone backwards, but with this prescription for star of k, then if we plug this into here and check the symmetry algebra, we recover exactly this initial symmetry algebra that we started with. And then the next thing we want to do is we want to gauge these symmetries. And the standard method to gauge symmetries is, in particular, zero form symmetries, but we can extend to higher form, but that's not important. So for these zero form symmetries, we can gauge them by coupling the uniform currents to gauge fields through some coupling like this. So we introduce some gauge field A, which couples via wedge product with star j, and then also an A prime, which couples via wedge product with star k. And yeah, we can do this without loss of generality. And this is consistent with the current conservation laws I mentioned before, if we impose gauge transformations like this, where all these terms are added. So for example, A prime has a standard gauge transformation that transforms us to some d of some lambda prime. But A is non-standard. It has the usual d lambda term, but then it also has a lambda prime dx term. But we need that in order to compensate for this extra term that we had in the current conservation law. So anyway, this is how it works out. And from these, in turn, we can construct gauge invariant field strengths. Again, since we have this non-trivial transformation here, our field strength for this A field is not just dA, but we also have to subtract another term to cancel this gauge transformation. And then this little f is gauge invariant. And f prime is dA prime is already gauge invariant. And then we have these fields, so then we can just write down their Lagrangian in the standard way. So f wedge star f, which is just the Maxwell Lagrangian in terms of in differential form notation.
It's not a remove invariant here, right? Because of this dx.
Right, this is in flat space. Okay, so where do the one form symmetries enter into this? So if we look at the pure gauge theory case where we just have this part and not these currents that we started with, but we just have this gauge theory. There are one form symmetries. In particular, I'll look at the electric one form symmetries. There are of course also magnetic one form symmetries, but in particular these electric ones look like this, which I have a curly Q for the integral of star f over some surface. And then there's a curly Q prime for, which is the integral of star f prime over some surface. But then to make this conserved, we need to include an additional term. And again, because we have this additional term with x times star of the other one, then these satisfy the same commutation relation as before, or a commutation relation of the same form. So px commutator with curly q prime is curly q.
So obviously, a commutator with EPY and EPZ with Q prime is 0.
Yeah. So everything else is trivial. Right, and then as we established for one-form symmetries, the charged object is a Wilson line. So in particular for this Q, the Wilson line you write down is this. So it's e to the I Q times the integral over some closed curve or infinite line over this gauge field little a. So, but remember we had this non-trivial gauge transformation law. So the Wilson line with this standard gauge transformation is gauge invariant. But if we have this non-standard gauge transformation with this extra term, and the presence of this extra term means that this Wilson line is no longer gauge invariant. So it's, if you like, it's no longer a well-defined operator in general. But the only time, because you get, when you do the gauge transformation, you get this integral over this c of lambda prime dx. And dx, of course, corresponds to the x direction. So what this means is that if we have any, if our curve has any, travels in any way in the x direction, then this operator is no longer a gauge invariant and doesn't make sense. So the only thing that makes sense is that this world line cannot have any trajectory in the x direction. So, and as we interpret this as, if we interpret this as a world line of a particle, it means the particle cannot move in the x direction. So it's confined to any directions, including time, that are transverse to the x direction. Yeah, and this is a closed loop, but we can also have an infinite, like something extending from infinite past to infinite future. So this is the basic idea. And now let's see how we recover the scalar charge gauge theory from this. So to impose mobility in all spatial directions, we do the same thing, where we have the commutator of pi and what I just called qj is some delta ij times q, with the minus sign is just a convention. And then we have an ordinary U1 charge q, which is the integral over star j over some m, some manifold, and then qi is the qi, where I is 1 to the spatial dimension, constitutes the dipole charge. And then we can write down this dipole current, so we can decompose this star ki into star little ki plus xi star j, and we have these kind of conservation laws exactly as before. And then we do the same procedure with each of these. So we have a coupling to gauge fields via an A wedge star j, and then we also have an curly A I wedge star ki, where there's an implicit sum over I, so over all the different directions. Where both this little a and curly a are one forms, but then this curly a has an additional spatial index I. And these have gauge transformations, like so delta little a just transforms as lambda. This is the ordinary U1 gauge parameter. But then there's an additional twist term, and then the curly AI transforms as d sigma I, where the sigma I is like the dipole, kind of like a dipole gauge parameter. And again, we can write down gauge invariant field strengths and a Maxwell-like Lagrangian. So when we go to low energies, and we define that as, so we've introduced some coupling constants here. So by low energies, I mean that the ratio between these coupling constants is such that some of the modes get an effective mass. In particular, these ones, they get an effective due to this term in blue here. When we look at f wedge star f, then this will give an effective mass for these modes. And this is an example of the inverse Higgs mechanism. And then, in addition, this delta little ai, the spatial component, can be fixed by a gauge transformation. So the remaining, at low energies, the remaining physical degrees of freedom are little a 0. Well, there is this ai, but we can fix that. And then the symmetric part of curly ai jth component. And these are not all independent, and the independent components are, we can identify this phi as a0, and then this capital aij as this symmetric combination here. And these transform under this ordinary U1 symmetry in precisely the way of this symmetric tensor gauge theory. So we've recovered this scalar charge gauge theory. And then in this case, the Wilson line has a gauge transformation like this, where this is the sum over every spatial direction. So this is only gauge invariant if there's no extent of this curve in any spatial direction. So this curve is constant in space, and thus the corresponding particle is a fracton. Okay, are there any questions about this part? Okay, maybe I will move on. Yeah, there's one other example, which is a vector charge gauge theory. In this you have a different commutation relation where you have now a vector of U1 charges, and you can consider commutation relations like this. And from this, the structure of this commutation relation, we can anticipate the result that particles with this charged under this vector of charges Q can move only parallel to Q, and therefore they're line-ons, so they can only move along the direction of this charge vector. And we can generalize also to higher multiples, and there are various other theories we can construct with this technology. Okay, now for something completely different, which is double field theory. So this is a totally different way of realizing fracton-like behavior. So double field theory, for people who are not familiar, so we double the dimensions of space-time. So we have some capital D dimensional space-time, but we describe physics using d plus d coordinates. And then we can write the double coordinates as capital A, which includes some ordinary x nu coordinates and some x tilde directions. And then double these indices A are raised and lowered using an ODD invariant like this. And when we do this, with this construction, we want to have various symmetries, in particular an OD comma D symmetry, which is a crucial element of double field theory, although it's not so important for this talk, but it's there. And we have double diffeomorphisms induced by a generalized Lie derivative on this double space. And the point of double field theory, at least its original motivation, was to make manifest the hidden so-called Boucher symmetry, discovered by Boucher, that maps different space-time backgrounds in the supergravity limit of string theory. And yeah, just briefly, when we double the number of spacetime dimensions, we're actually, in the end, if we want this to be consistent, we have our double diffeomorphism algebra has to be closed. And we ensure that by imposing something called the section condition. So the theory is consistent if partial A is 0, which means that partial tilde mu is 0 on any fields. And we can simply solve this, satisfy this condition by saying that partial tilde mu is 0 on anything, so all fields are independent of the x tilde coordinates. So this is not a true doubling, it's just repackaging whatever d-dimensional physics. And it's related to the level matching condition in string theory between the momentum modes and winding modes, if you think of compactifications in T-duality. But that's not important right now. So the main ingredients of double field theory are, there's a DFT dilaton, which provides a volume element for every action. This is important for ODD symmetry, but it's not so crucial here. And then there's also an ODD and symmetric DFT metric HAB. And from this, we can construct a so-called semi-covariant derivative, as well as fully covariant geometric objects like the Ricci tensor and Ricci scalar, and double field theory versions of those. But the point of all this is that on what we call Riemannian backgrounds, by which we just mean usual spacetime, from this we want to recover usual spacetime. And then with this section in choice, the DFT variables are just identified with the closed string massless sector, which is the spacetime metric. Then there's an antisymmetric rank 2 tensor B field, and there's a scalar field called the dilaton. And this D and HAB precisely reduces these fields such that this volume element decomposes like that. And importantly, this HAB has the inverse metric and the B field all packaged together. So this is very nice. But yeah, one more thing is that we can also couple to additional matter. So this DFT Ricci scalar gives the gravitational part of the Lagrangian. And if we have any additional matter, we can write down an ODD covariant Lagrangian for that matter. So we have something of this form. And when we vary this theory, we get a DFT generalization of Einstein's equations, or Einstein double field equations. And this DFT energy momentum tensor is conserved on shell when the equations of motion are satisfied, and has additional components giving source terms for the B field and dilaton. So this is all very well, but double field theory turns out to be more general than just the theory of G, B, and phi. So it also has non-Riemannian solutions. And in such cases, the usual inverse spacetime metric becomes degenerate. And it follows that the corresponding metric would be singular, but actually in the DFT metric, HAB, there's no singularity. And everything is fully regular. For example, a trivial or almost kind of trivial example is the maximally non-Riemannian solution, where we just set this HAB to be plus or minus JAB. And this, recall this JAB is just this off-diagonal blocked identity matrices. So with that, then the theory is fully ODD symmetric, and there's the space of fluctuations of this theory is then trivial. And we can express a general non-Riemannian solution by like this, and for simplicity, I factored out the B field. It's some kind of additional ODD rotation. But the main ingredient is the central part, where we have an H mu nu and an M mu nu on the diagonal elements, and these are both degenerate, and they have n plus n bar null eigenvectors, x bar and y bar. and this z here is just a combination of those. So having these, when we have these off-diagonal components, this is a hint of having non-Riemannian geometry. So depending on these two non-negative integers n and n bar, we can get various Riemannian and non-Riemannian backgrounds. And some examples are 0, 0 is just usual Riemannian or Lorentzian spacetime, where we recover the metric in its inverse, and this z mu nu equals 0. We also have like Newton-Cartan spacetime, which is like Lorentzian spacetime in the limit where the speed of light goes to infinity. And there's also Carroll spacetime, which is the more exotic seeming case where the speed of light goes to 0. And there's further examples like 1,1 corresponds to things like the non-relativistic string by Gomis-Onoguri, and torsional Newton-Cartan spacetime as well. But for now, let's just look at a very simple case. So we'll consider flat non-Riemannian backgrounds with a general n and n bar, and we just set the B field to 0 and the dilaton to be constant. And then we just decompose our coordinates, x mu, our regular coordinates, as into xa, which are where a runs from 1 to little d, and this is the maximal Riemannian subspace. And we have a non-degenerate Minkowski metric eta ab on that space. And then yi and y bar I bar span the non-Riemannian directions. So then the components of this HAB are just like this. So we have h mu nu is eta ab in this top part here. KAB is, or k mu nu, sorry, is also eta ab with lower indices, the lower index Minkowski metric. And then z mu nu has Kronecker deltas on the non-Riemannian directions. And the I and I bar directions differ by a sign. Yeah.
So in this flat case, you recover Minkowski.
Yeah, I mean, so we have Minkowski, we have some, the Riemannian part is Minkowski.
So in the previous slide, you showed that there is a torsional Newton-Cartan spacetime.
Mm.
So I don't know, like suppose we have a theory in that non-Riemannian spacetime, then it should be an enhanced theory of what is known in the torsional gravity field, right? I don't know, like which contains the B matrix effect of B minimum.
Yeah. I think it should. Yeah, so here we just have a very simple example. Right, so non-Riemannian backgrounds have some nice exotic properties, and we can consider the simple case of a point particle. And we can write down a double field theory action for a point particle. It's just something like, so if tau is a parameter that is like the proper time of like the parameter that moves along the particle world line, we have something like d tau xa, d tau xb, HAB, and we can have some mass term as well. And this capital D, this bold capital D, is just, it's d by d tau of, so one part is d by d tau of x nu, and then there's another part which is d by d tau of x tilde nu minus some a mu, which is some, and this is some, we can think of this as some kind of intrinsic gauge field, and this is the double de-gauged covariant derivative. But if we just once we impose the section condition, we pick out this part essentially, and then normally we just get the usual point particle action from the this would give us the inverse metric here, I think, G mu. So you get G mu nu dx mu by d tau dx mu by d tau or something like that. But if we do this on an n bar non-Riemannian background, we get this usual term, which in particular, looking at the simple example I showed before, we have some x dot a term, and the mass term comes along, but then we also have something that looks like lambda I, y dot I, and lambda bar, I bar, y bar dot I bar. So basically we have these terms linear in the velocity in the non-Riemannian direction. And this lambda and lambda bar, these act as Lagrange multipliers, and they enforce that y dot is 0 and y bar dot is 0 for this particle, which means the particle is frozen along the y and y bar directions. So this appears to enforce restricted mobility. And yeah, so as we've seen, this covariant action for a point particle becomes linear in velocity and along the non-Riemannian directions. And this implies the particles cannot move in those directions. And another thing is that non-Riemannian flat backgrounds have infinite dimensional isometries. So if we solve the Killing equations, the Killing isometries are something like this. So we have something like WAB, which correspond to Lorentz transformations. But then in addition to that, we have a whole bunch of other terms. In fact, we have a whole function's worth of parameter space, which means infinite dimensional parameter space. And this we can identify as so-called super translations. But in any case, what we find is infinite dimensional isometries. And in double field theory, there's also a notion of conserved charge, which is related to the DFT energy momentum tensor like this. And for generic NN bar flat backgrounds, we get a conserved current, which is related to the different components of the DFT energy momentum tensor and is conserved. So this is basically just this. And then explicitly in this non-Riemannian case, for this previous infinite dimensional isometry, we get this current having all these terms with these infinite dimensional functions. So, and then if we take the linear term of these functions with coordinates, we can get things like that look like dipole currents. So in addition to like global translational symmetries and Lorentz symmetry, this omega in particular has this linear term here, which generally generates dipole conservation. And then other functions, if they're present, would also generate higher multiple conservation laws. So it seems there's a correspondence between practons and non-Riemannian double field theory. So practons have restricted mobility, and this is reflected by geodesic immobility in non-Riemannian double field theory. Practons have this Brown state degeneracy, which is reflected in the infinite dimensional isometries of in non-Riemannian backgrounds. And then the dipole higher multiple symmetries are related to the conserved current, which is polynomial in the non-Riemannian coordinates. So the main message number 2 is that multiple symmetries and mobility restrictions present in Fracton models may correspond to the infinite dimensional isometries and particle immobility that's present on non-Riemannian backgrounds of double field theory. So then the final thing is to return to this question of what fractons really are. So there are a few interesting things that are happening in current research. One is that fractonic gauge theories. I mean, we have a symmetric tensor gauge theory, and this turns out to be closely related to linearized gravity. So we find that you can find that some part of these fracton gauge theories, Lagrangian, is some part of it is the linearized gravity Lagrangian, but then there's an additional pure fracton piece as well. So another thing is that Carroll geometry. So this, as I said, is the C going to zero limit of Poincare geometry. And this corresponds to this D-1, 0 non-Riemannian double field theory. And in Carroll geometry, light cones close up because the speed of light is 0. And particles, if they're not tachyons, the particles in this theory cannot move. So this is very suggestive that Carroll geometry is something like an infinite multiple fracton situation. And on top of that, the fracton algebra is actually isomorphic to the Carroll algebra if we identify the Carroll boosts with dipole symmetries. But this is just at the level of the algebra. And we identify the U1 charge as the Hamiltonian. So there seems to be some non-trivial correspondence there. Another connection is that elasticity theory is related to the fracton gauge theory by a duality transformation, which was shown in 2017. And furthermore, we found that the double field theory version of Yang-Mills theory, so because we have a doubled vector, if we have a doubled vector potential, we have twice as many components. So one half of it is just the usual vector potential, but then we have another like D set of components. And it turns out that looks like a phonon vector. So we get something that resembles ordinary Yang-Mills theory plus an elastic strain tensor. So this is another interesting correspondence with both condensed matter physics and also fractons via this duality. And yeah.
In this elastic theory, you have non-Riemannian parameters.
So this is actually independent of whether we have Riemannian or non-Riemannian geometry. Yeah. So yeah, we can have. It's just in any case the Yang-Mills theory has all these additional components, and we can have. We can have ordinary Riemannian Yang-Mills. We have non-Riemannian Yang-Mills. We can have Riemannian elasticity and non-Riemannian elasticity. And in addition, some singularities in GR, in general relativity, correspond to regular non-Riemannian geometries, which could be, which is interesting in light of the possible correspondence between fractons leading to some emergent gravity. And then double field theory also includes higher multiple isometries, which might suggest that there's couplings not just to a rank 2 symmetric tensor, but also to higher rank symmetric tensor theories, for example, in higher spin gravity. So there seem to be many connections to gravity and singular limits. So I'll leave you with the question of what are fractons? Yeah, and this is my summary. So yeah, I'll just say briefly, fractons are novel particles with restricted mobility. Gapless fracton phases can be obtained from spontaneous symmetry breaking of non-uniform higher form symmetries. And we get mobility restrictions from the symmetry algebra and through constraints on the world lines of charged particles. And then on the other hand, if we go to double field theory and non-Riemannian backgrounds, where the space-time metric is singular, but double field theory is regular, along non-Riemannian directions, we get infinite dimensional isometries, leading to higher multiple conservation laws, and point particles cannot move in those directions. So there's all sorts of connections between fractons, symmetric tensors, gravitational singularities, non-Riemannian geometry, and higher form symmetries. And this suggests a bigger picture that's not yet fully understood. Thank you very much.